The pH analyzer represented here has two electrodes which are submerged in a beaker of solution. The electrodes and the beaker of solution form what is known as an electrolytic cell. The two electrodes are connected by wires to a measuring device that has a pH indicator. The principle of operation for this pH analyzer is based on the fact that the electrolytic cell will produce a voltage in relation to the pH of the solution. The ions that are present in a solution have an important characteristic: the ability to conduct electric current. The ease with which electric current flows through a solution is the solution's conductivity. As the concentration of ions in a solution increases, that is, as the solution becomes more concentrated, its conductivity increases as well. For that reason, the concentrations of some solutions can be determined by measuring their electrical conductivity. Oxygen concentration measurements can be important to many industrial processes. For example, oxygen analyzers are often used to measure the percentage of oxygen in boiler flue gases. Plant operators and control systems can use those measurements to maintain proper boiler operation. One type of oxygen analyzer that's used in industry is a paramagnetic oxygen analyzer. It operates on the principle that oxygen is attracted to a magnetic field. The paramagnetic oxygen analyzer represented here has a sample chamber and two sets of magnets, each of which creates a strong magnetic field. Suspended between the magnets is a glass test body or measuring device with a mirror attached to its center. The mirror reflects light from a light source onto a scale which provides a visual indication of the oxygen concentration of a sample gas. During operation, the gas being measured enters through the chamber's inlet. The oxygen in the gas is attracted to the centers of the magnetic fields and tries to force the spheres of the measuring device out of the magnetic fields. Looking down from the top, we see that this causes the measuring device to turn, which changes the angle at which the light hits the mirror. The point on the scale where the light hits indicates the percent oxygen value of the gas. Often it's necessary to monitor the concentrations of gases other than oxygen in a gas mixture. For example, many plants measure the concentration of a specific gas in a binary gas mixture, which is a mixture of two gases. An analyzer that's commonly used for this purpose is a thermal conductivity gas analyzer. Thermal conductivity is the ability of a substance, such as a gas, to conduct heat. The operation of a thermal conductivity gas analyzer is based on the fact that different gases have different rates of thermal conductivity. Argon, for instance, has a lower thermal conductivity rating than nitrogen. By measuring the thermal conductivity of a binary gas mixture, it's possible to determine the proportions of the gases in that mixture. For example, this thermal conductivity gas analyzer measures the concentration of argon in a binary mixture of argon and nitrogen. The analyzer has a meter and indicator that's connected to a thermal conductivity cell. The cell contains a sensing element or wire whose electrical resistance is sensitive to temperature change. During operation, electric current is passed through the wire, causing the wire to heat up. The analyzer is calibrated so that pure nitrogen will have virtually no effect on the temperature of the wire or the reading on the indicator. But when an argon-nitrogen mixture enters the cell, the argon causes less heat to be conducted away from the wire, and the temperature of the wire increases. The amount of increase depends on the amount of argon in the mixture. The temperature rise in the wire also increases the resistance to current flow through the wire, which in turn reduces the amount of current flow through the meter. The meter converts the change in resistance to a visual indication of the percentage of argon in the mixture. Some of the gas mixtures in industrial processes are complex gas mixtures. They contain more than two gases, and in some situations it's necessary to measure the concentrations of the gases in these mixtures. One way to do this is to use an analyzer called a chromatograph. The chromatograph in this simplified illustration consists of a sample gas inlet, a supply of carrier gas, often helium or air, that's used to move or carry the sample gas, a tube or column that's filled with packing material such as activated carbon or silica gel, a thermal conductivity cell which measures the concentration of a gas in a mixture based on the gas's ability to conduct heat, and an indicating device, in this case a recorder. During operation, a sample of the gas being measured is fed into the chromatograph through the sample gas inlet. The carrier gas is then used to carry the sample gas through the column of packing material. Different gases flow through the material at different speeds. So the packing material separates the sample gas mixture into its individual gases. The separated gases then leave the column with the carrier gas and flow through the thermal conductivity cell. The identity and the concentration of each individual gas can be determined by how long it takes the gas to flow through the column and by its effect on the thermal conductivity cell. The recorder provides a visual indication of these measurements. The carrier gas is taken into account when these measurements are made. In this topic, we focused on the measurement of oxygen concentration, non-oxygen gas concentration, and complex gas concentration. Now let's try some practice questions that relate to this material. During operation, the gas being measured enters through the chamber's inlet. The oxygen in the gas is attracted to the centers of the magnetic fields and tries to force the spheres of the measuring device out of the magnetic fields. Thermal conductivity is the ability of a substance, such as a gas, to conduct heat. The operation of a thermal conductivity gas analyzer is based on the fact that different gases have different rates of thermal conductivity. Argon, for instance, has a lower thermal conductivity rating than nitrogen. By measuring the thermal conductivity of a binary gas mixture, it's possible to determine the proportions of the gases in that mixture. Some of the gas mixtures in industrial processes are complex gas mixtures. They contain more than two gases. And in some situations, it's necessary to measure the concentrations of the gases in these mixtures. One way to do this is to use an analyzer called a chromatograph.